So good afternoon, everyone. Welcome to today's data learning seminar. So today we're very happy to have Professor Max Welling from Microsoft Research and University of Amsterdam. So Professor Welling will give us a talk about using deep learning to better understand science. So I will leave the audience with you, Professor Welling.
Thank you. Yeah, so I'll talk a little bit today about deep learning applied to sciences, and I would encourage people to interrupt with questions if they wish to. It makes it nice and interactive. We have a total of 1 hour, and we can fill it, but I don't need to finish my slides necessarily. So feel free to ask questions in the middle of the talk. So these are the brilliant students who helped me with all this research, or they were actually the main drivers, I should say. Yeah, so it's a lot of them. They're all fantastic. And if you want to read more about equivariance, then this is a great thesis to read by Takov Cohen, and this is a paper by Maurice Weiler, which is very beautifully illustrated, which you can also read on the topic. So here, by the way, is one of the pictures that he made. Kind of beautiful. So the overview is going to talk a little bit about symmetries and equivariance, about graph neural nets, about equivariant graph neural nets, and then how you can apply those to molecules. And then I'll talk about solving PDEs with GNNs, which is sort of a more recent application of GNNs to PDE solving, numerical integration, and then I'll conclude. So first a bit about symmetries. So symmetries are really beautiful organizing principle in physics, a truly elegant way to unify the equations of physics. For instance, around the turn of the previous century, James Clerk Maxwell unified magnetism and electricity into electromagnetism by just understanding how different observers can transform electric fields into magnetic fields. So here's one observer, Joe, standing still and is seeing an electric charge. And then Jane here is moving with a certain velocity relative to Joe and sees an electric magnetic charge, right? And so also similarly, an electric magnetic charge can also be sort of removed and turned into an electric charge. So that's a symmetry of the world. Basically a symmetry that there's different ways, relative velocities that observers should be able to describe the world, but the phenomenon, the underlying physical phenomenon, doesn't actually change. It's just your description of that changes. The coordinates that you use to describe it change. And sort of another example is general relativity, where there's sort of a symmetry between gravity, like this guy here in a box throwing a ball to the ground, interpreting it as gravity. And this guy here in a rocket that is accelerating sees exactly the same thing. But this person would sort of interpret it as, basically acceleration. Now, if you can't look outside, these two situations are indistinguishable from each other, which means, again, that there's a symmetry. And this led, for instance, to the whole theory of general relativity, to consider, what happens if you look at accelerated frames, not just frames with a constant speed, but actually accelerated frames. And also in quantum mechanics and quantum field theory, it's all organized around symmetries. So the basic particles like quarks and leptons, they're all representations of certain groups like U1 and SU2 and SU3. And so by a symmetry operation, you can turn one particle into another particle. Now, in deep learning, you actually have something quite similar. You can sort of imitate the situation by noticing that the prediction that a neural network makes, let's say the class of sort of skin lesion on the left-hand side that you try to classify, or maybe, the diagnosis, whether there is a cancer or not in this image on the right-hand side, doesn't really depend on the orientation of the camera with which you made the picture, right? And so that's an invariance. Now, if you were doing sort of segmentation here, then the segmentation mask should rotate with the rotation of the input, which is what we call equivariance. And I will, of course, talk about that more now. So equivariance is a very general concept that we're going to sort of use in the internal guts of a neural network. It's a structure that we impose. The structure is that if we have some signal, it could be, typically it's on a line or a plane, but, just here we put it on an egg. So the signal is a gecko living on an egg. And we're going to analyze this sort of signal living on this manifold. And we do this by convolving with a particular filter. Now, you do this on an egg is, of course, a bit detailed, but we, think about, some kind of filter operation that you would do where the filtered output is actually this sort of image here. It's sort of an edge detector, as you can see. Now, the symmetry is that, if I rotate the gecko, let's say, around this axis here, so you can see the space is sort of symmetric, then if I first rotate and then filter, I should get the same result as if I first filter and then rotate in this space here, this sort of latent space. And this operation can actually be different than this operation. It doesn't have to be literally the same, as we'll see in a minute. But the closing of this diagram is what we call equivariance. So you can think of this as a sort of segmentation mask. And intuitively, of course, this makes a lot of sense. But for if you take an MLP and you apply translation symmetry, you get sort of a CNN, so convolutional neural network. You reduce the number of parameters from n squared, where n is the number of neurons in the input and output layer, to maybe 9, or times the number of channels, where 9 is sort of the filter size, and then times the number of channels that you have. So a huge reduction in the number of parameters. So the same thing happens here. In order to enforce these types of symmetries, we're also going to get a huge reduction in the number of parameters. And that actually helps with data efficiency. Now, there's less degrees of freedom that we will have to learn from data. And that makes you learn more efficient from the data that you have, because you are basically imposing a sensible inductive bias on your problem. Now, the other thing is that it actually creates an interesting structure in the hidden layers of a neural net. And Jeff Hinton calls these capsules, and they come out very naturally from this sort of procedure, as I will show in a minute. The capsules will, for instance, be different orientations of these filters stacked in sort of a channel dimension. And that sort of that set of filters, one for each orientation of the filter, is what we then call a capsule. It's also good because the next layer, which looks at these images, now have again a very structured signal to look at, right? Imagine that by rotating, so this is the unrotated, and now by rotating, this would be a completely random scattering of these pixels. The next layer would have a very hard time figuring out what to do in this rotated version of the input image if it sort of had learned something for this version of the image, right? Because this would look completely different now. Where if things are equivariant, the next layer would have a much easier job. It has to be equivariant as well, to just know that these two things are actually just the same situation. Now, there's one additional property which I call abstractions preserve symmetries, which mean that if so here I sort of take a face, which is just a bunch of pixel values, and I rotate the face. And I do this for two faces, but these two faces map to the same sort of abstract face, right? So as a neural network, what it wants to do is abstract things, right? Into object categories, for instance. So here's an abstract face. And now it turns out that both of these rotated images under the same group transformation also map to the same rotated abstract image of the original image, right? And so that's also a desirable property. So in sort of more mathematical language, equivariance can be written as follows. So if I have a map that maps from X to Y, so from, let's say, input to some hidden layer, and I have a function which transforms under sort of symmetry transformation, transforms in X space and sort of an associated transformation in Y space, then we say something is equivariant if I first transform X space and then filter, or I first filter and then transform in Y space. And that is precisely corresponds to the closing of this diagram. Now, in somewhat more detail, so first of all, here is illustrated how sort of this is a normal convolution, right? Where you take a filter, you move it over an image, and then you take the inner product of the underlying image and the filter values, and you then add everything up and store it here. Now, the same sort of operation we can do, but now for all 4 orientations of the filter, and we then store the results at 4 different channels of the orientations. Okay, so how does that look like? So if I take an input image and I sort of have 2 types of capsules. One is an eye capsule that sort of tries to detect the eyes here. One is a mouth capsule that tries to detect the mouth, right? And then in this particular orientation, I find that these first sort of detectors fire, and all of these are at the wrong orientation, so they don't fire. Now, if I rotate the image, then in fact, now the next sort of set of these filters will fire. So now what I have is I have a sort of a rotation of the input, so the rotation of the features of the filters that fire, but also a shift in this sort of capsule dimension to the right. So the operation in the latent space here is actually different than the operation here in the image space. And sort of already Jan de Koen on his webpage shows how a CNN is actually translation equivariant, like here, but it is orientation non-equivariant, because if this thing rotates, and these are the feature maps, you see that they don't only rotate, they also have some strange transformation that's happening on the edges here. And here's a nice visualization by Daniel Worrell, where sort of, you take a particular input image and you start rotating it in front of the camera, and here you sort of stabilize the image. You can see that for a non-equivariant CNN, these sort of latent filtered representations, they do change. And for the ones that are sort of the equivariant neural network, it's stabilized. Now, if you're interested...
Can I just ask a quick question?
Yes, hi, Mark.
Hi, Max, nice to see you again. So in the stabilized version, you must also rotate the image into a canonical orientation.
Yeah, that's just for visualization in some sense, right? So, yeah.
Right, okay. So maybe I have another question on this topic, but I'll do that later.
Okay, yeah. So basically, this is what's happening here is going on. So you have one neural net that sort of looks at this thing from one orientation, and then you rotate the input image at it, right? And then the filtered images, they change, right? And in order to not have to turn your head or your computer around, we sort of stabilized sort of the image here.
Makes complete sense. Thanks.
All right. So if you're interested in this, but don't want to dig too deep into the math, there is very nice software written by Mark Finzi. And basically what you need is some idea of the representations for your input and your output layer, which could be vectors or tensors or things like this. And you also need to know the generators of your group. So for instance, for the permutation group, there's, I think, n-1 generators. So very few generators for a group which is like n factorial large, so a huge number of group elements. Still, the number of generators is low. And here the Rubik's cube group is actually even more ridiculous. There's 4 to the 10 to the 11 elements, but there's only 6 generators. Actually, I'm not sure if it's more ridiculous, but it's certainly a huge number of group element versus a few generators, which means that you can just stick this particular group into the software, and you then get all the kernels which are equivariant, right? And then you can linearly combine these kernels to get an equivariant layer, and you can learn the coefficients that multiply these kernel values. Okay, so the next, what I want to go now is molecules, which is something I'm very interested in more recently. So, so molecules are fascinating in a way because almost everything around you that you can touch, right, is made of molecules at some level. Now, there's electromagnetic waves like light and gravity and some nuclear forces that are not made of molecules or matter. Those are, gauge fields. Or plasmas, where basically you've ripped molecules apart and sort of removed their electrons. And or if you go deeper, you can even sort of go into sort of the structure of a nucleus, and you'll find quarks and all these kinds of things, right? So there is structure below it, but all matter at some point is made of molecules. Yet, and actually the physics is very well known, so we understand all the equations, but they are in essence, certainly the electrons are quantum mechanical. You have to treat them quantum mechanically, which means that's actually in order to solve the Schrödinger equation, that's NP hard. It's a really difficult problem. So it's very hard to actually simulate molecules very accurately. And so even though we understand the laws of physics and they're everywhere, simulating these molecules is super hard, and we can only really do it super effectively for small molecules. But if we could simulate these molecules really well, we would be able to solve, or at least make progress on a whole bunch of really important problems. I'll go through a few of those here. For instance, in drug discovery, right? If we understand how a particular sort of small ligand, let's say, would bind to a large protein, then you can try to design this as a drug to sort of disable sort of the protein that may cause a disease or something. Right. Also, turning light into electricity using photovoltaics, solar panels, let's say, also goes through molecules, right? So the light comes in, it sort of does something to these molecules, which generates energy, which you can then store or turn into electricity. I've heard that 20% of all sort of energy gets dissipated through friction, which is a lot, like 20% of all the energy. And so if you can build more effective lubricants, you can sort of bring that number down quite dramatically. There was this very nice OC20 sort of competition organized by Facebook and CMU, where they had a very large data set of what's called density functional theory calculations, which are sort of quantum mechanical calculations, to compute how a small molecule would relax onto the surface of a metal, which is like a catalyst. And those calculations, you can try to predict with machine learning, and they are very useful in order to design, let's say, the best possible surface here in order to catalyze, certain reactions, like, for instance, hydrogen production or carbon capture. There's nitrogen fixation, which is important for producing fertilizers, also a very dirty process where lots of carbon dioxide gets emitted. And of course, there is, the ambition to understand the human body or the human cell, where you have like thousands and thousands of proteins all interacting in very, very complicated ways. Now, the physicists have built themselves a sort of huge microscope, you could argue, to look at the tiniest bits and pieces of the universe. And that's called, of course, a particle collider, or the LHC, Large Hadron Collider, that's currently active at CERN. The astronomers are building themselves a huge telescope to study, science. For instance, this is the Square Kilometer Array, which is built in different continents. Part is in South Africa, part is in Australia. There's also parts in Europe, and they're all sort of combined in very sophisticated ways to create one signal, to study sort of signals, radio signals coming out of the sky. Now, in chemistry, sort of we argue that what we really need is sort of a computational microscope, where we can start to simulate molecules using quantum mechanics and machine learning in order to better understand their properties and predict properties, and in order, for instance, to design new drugs and new catalysts, etc., etc. So what's interesting is that, for instance, when we design airplanes, what we typically do is we do it by trial and error. And so we first build an airplane and then try to fly it. And if it crashes, bad luck, you have to, change something and try again. In sort of later era, people would build sort of models and put them in wind tunnels, collect a lot of data and use that data to create, to design an airplane. These days, airplanes are basically completely designed in silico, in a computer. And basically the only, that you can completely design them and then make them and then fly them. And then basically that's almost, it almost never crashes after that. And of course, the amount of compute that you need in order to do the entire design in a computer is like growing exponentially relative to the other approaches. Something similar is actually happening for molecules. So in molecules, you also start by trial and error. So people started by just putting a whole bunch of things in a reaction and seeing what come out and testing it. Then people did lots of data-driven models where you do lots of things, you measure lots of things, and you put it in a database and you train sort of empirical models based on all that data. And the last thing is ab initio type of simulation of nature by sort of solving Schrödinger equation and molecular dynamics and basically moving the atoms through space and measuring their properties in a computer. And again, you need a lot of compute to achieve that. Now, what are the key challenges that need to be solved in this field? Well, there is, of course, that we need to get a lot more accurate in these computations. And of course, here the big blocker is quantum mechanics. It's an exponentially hard problem, so we need to be very smart in the way we do approximations. The other blocker is chaos. So if you try to have, a whole bunch of atoms and, let them freely sort of move around under the forces of basically classical mechanics, that is a chaotic motion, highly nonlinear chaotic motion, because these atoms interact with each other and they interact with the electrons, etc. It happens at the scale of femtoseconds, right? So at the scale of a femtosecond, there are significant changes in a molecule. And so it's just extremely hard to get anywhere with sort of trying to simulate this in a computer and sort of to wait, let's say, until a particular reaction happens. So you really have to shortcut that computation. And then the last thing is we want to study large systems of atoms and molecules, which means that we have to do some kind of coarse graining. For instance, if we look at the cell, we might want to look at billions of atoms at the same time. Now, clearly, that's unmanageable in a computer, so you will have to do smart approximations to coarse grain these things. So a little bit more detail. Of course, you have sort of an atom. We sort of like to represent that as a graph where there's positions for all of the atoms. The atoms have a certain color, the type of atom, they have a particular charge, there's electrons around it. Now, some of these electrons are bound to an atom, but some of them are sort of much more freely floating around us, like a cloud of things. And then there's, of course, forces. If two atoms get close to each other, we get sort of the Lennard-Jones sense of potential, and there's torsion forces when things are rotating, etc. Right? And these angles full of forces. So there's lots of forces on this thing, and we just use classical mechanics to move this forward. Typically in a solution, which means there's a lot of jittering of these atoms going on, but in principle, it's just classical mechanics. The only problem is that if I, in order to do classical mechanics, I need to compute forces. In order to compute forces, of course, I need to look at all the other atoms. That's not a problem. But what is the problem is there's this electron cloud around it. And in order to compute the forces due to the electrons, you need quantum mechanics. And that's a really, really hard problem to solve. So come sort of machine learning to the rescue. We know how to do machine learning or deep learning on graphs. So we model the molecule as a graph, and we send messages over the edges of a graph. And so basically we want to input the positions and the charges and then we want to predict, let's say, the ground state energy or other properties of this molecule. And we just treat it as a message passing scheme on this graph where atoms interact with neighboring atoms. This one could also interact with this atom, of course. Send messages and update their positions and update their, their properties, or basically you go through a number of layers of graph message passing to predict certain properties of this atom. So a little bit more about graph neural nets. So I assume you sort of know about convolutional neural nets. So you take an input image and you sort of have filters that you move over these input image. You get filter maps. You have pooling operations. Pooling operations also, you also apply filters to it, etc. And then at the very end, you sort of flatten the entire vector that you have into a big sort of flat vector, and then you apply an MLP to make a prediction. Now, these convolutions look like this. I already showed this image. I won't explain it again. So that's sort of a convolution. We can understand a convolution more or less as a message passing algorithm where now here at every position, let's say pixel position, there is a vector and a feature vector. So that's basically slicing through this stack of, of channels here like this. So that's the vector that's living here. And in order to update this state here, you're sort of changing, you're multiplying each one of these feature vectors with a matrix. Could be a different matrix for each position. You add everything up and then, push it through nonlinearity, and then you get your new value here. For a graph, it's very similar, except for the fact that the number of neighbors can change, as well as the ordering is undetermined. And so you will have to do something that is order independent. And that's solved by basically using the same message here. The red W1 is the same now, it doesn't have different colors. There's a slight generalization of this, which is written here, which is also a message passing scheme. So you have the feature vectors HI and HJ living on, let's say two nodes. There's some fixed information, let's say, living on the edge. It doesn't transform. There's a neural network. So you first compute a message for, let's say, I to J. Then you collect all the messages together. And then finally, on this particular central node, there's also a message, or a neural net that combines the message, some fixed information on that node, as well as your state on that node, push it through a nonlinear neural network to then get the new state at that particular position H. You iterate that, and in the end, you can predict something. So now the next step is
Can I perhaps ask another quick question here?
Go ahead.
So can you go back to the previous slide for a second?
Yeah.
So this is helpful for me to maybe commit something about graph convolutional networks to memory, hopefully forever this time. Can I see the neural network that encodes HI and HJ and the edge? Is that encoding necessary to essentially encode properties of those nodes, which is not necessary in the normal convolutional case because it's sort of easier to operate directly on pixel values? Is that sort of how I should see the motivation for adding that neural network there?
Yeah, so it's a slight generalization. I think so a convolution on a plane is super efficient, right? And that's why we use convolutions like that. But if you're just after, let's say, invariance under translations, you can also organize it slightly differently. And that's sort of this update. You can also think about it. So first of all, the generalization here is that for convolution, for this message, it usually depends on HI and it doesn't depend on the receiving node. And it's sort of a linear update. So there's a matrix which multiplies this H, but it is the same matrix. And here's the same nonlinear function phi E. Mm-hmm. But you can see that this thing is, okay, then you collect all the messages together. And so this operation is independent on the order in which you sort of process all of the neighbors, right? So that as an actual invariant sort of operation doesn't depend on the order. You can also still apply it if the number of neighbors change. Mm-hmm. But this is a generalization. And then there's another nonlinearity happening here on the node itself. That's just, I think, the usual nonlinearity that we think of, right? So that's per pixel values, and you now have some information collected here. So here you have sort of the same, you've collected information to the central node, and then you push that through a nonlinearity to get the value at the next level, and the nonlinearity x per pixel. So the generalization is there's a nonlinear operation here instead of a linear operation, and it depends on both the sending and the receiving node.
Okay, so perhaps I can adjust my question slightly. So I think I understand graph neural networks from the motivation of what's different about a graph compared to an image, and therefore I kind of understand what kind of changes you need to add. However, what I don't understand is whether that generalization that you do in the graph neural network, whether that can be backported to the normal convolution.
Absolutely. So you can do this here too, because this is more general than this. Well, of course, here this is more general because every neighbor can now have a different message, which would mean that this neural network here can be different for every neighbor, right? So but you could organize these computations or generalize these computations in a way that looks much more like a GNN update, where you would then make this phi different for every neighbor. The reason people don't do that is that not very efficient.
Okay.
Right? Because basically, a graph neural net, I guess you could do it. You can process everything in parallel, but matrix vector multiplications and things like and convolutions you can do very efficiently with modern hardware and software, right? And so that's why this is a super efficient way of doing things. But both these sort of are translation equivariant. Yeah.
Great.
Actually, this is also permutation equivariance. So this is even more symmetric than this one. But we could also make this translation equivariant, but using a more general update. Yeah.
Great. Thanks.
Okay. So then so then we're going to combine two things now. So now we're going to combine the graph neural net with the equivariance, and of course the motivation are now the molecules. So take a molecule, and we're gonna again put the nodes, make it the atoms or the nuclei, and then sort of the edges, basically if they're sort of connected. And then there are some scalar features, which are these blue bars here, which sort of represent scalar numbers that don't change if we rotate the image. And then there's some vector things, like think of forces which are acting, or velocities which are acting on these atoms. Now, equivariance basically means that if I first sort of filter or send messages on this graph, right, I get some different values for the functions on the nodes. For instance, all my scalar features will change and all my vector features will change. In fact, also the positions of these nodes might change, right? X is also a feature here. Now, I'm going to say that equivariance means if I rotate this thing around, if I rotate, this particular scalar set of features here rotates here, and you see it doesn't change at all. The vector, though, rotates with the frame, right? And of course, this point also rotates to this point. So we know precisely what to do when we rotate, a molecule. But then I'm going to say that if I first filter and then rotate, or first rotate and then filter, then these things will have to get to the same answer. And I can sort of go into details of how we do that. So let me briefly do that. So the updates that I just discussed now condense to this form. This is a limited form. This can be generalized, but this is very efficient and fast form. So the first thing is now the function that we just discussed with Mark is basically this nonlinearity, or this neural net. Now, doesn't only depend on scalars under rotation. It also depends on, let's say, the distance between two atoms, which is also a scalar, and other scalar quantities which don't change. Right. Then we have an update on the vector quantity, which, one way of doing that is basically to say, well, we sort of have a velocity. We take some nonlinear function of all the scalars, they times the old velocity plus, let's say, the difference between xi and xj times another invariant function. So this is one way of doing it. And you can see it's a vector because these things don't transform, but these two things are vectors. So we just take a linear combination of vectors, which is again a vector. We then update the positions. If we interpret this as a velocity, we then just move the particles around, given their velocity. And then the rest is just a GNN. So we collect messages and we do an update on the node. So these will remain scalars and these will remain vectors. So this is a very simple one. You can go much more complicated. I'll show very quickly some in a minute. But This is certainly equivariant, and it certainly has more than just scalars. So the SE3 transformer is more sophisticated. There's Mark.
If it's okay, I've got one.
Yeah, go ahead.
So it would be, can you just confirm something for me? So I'm trying to understand the kind of similarity and the difference between this type of equivariant neural network and the type of equivariant neural network, as, for example, of your paper with Taco in 2016, I think, the graph, group equivariant stuff. So it seems here like what the equivariance is in the actual values of neurons, right? So you want this vector, which you represent by two numbers, you want that vector to rotate in the right way, whereas in the original group equivariant paper, you wanted the activation pattern to rotate in a particular way.
Well, it's actually pretty close anyway, because if we would put these on a grid, these points, we would put them on a regular grid, right? Then the rotation of the image would be actually this rotation of these X values, these X nodes. That would be sort of the rotation that you would apply. And then in a neural net, you have the channels. So the channels inside a capsule form a vector of some kind. Now, in this case, we use a very simple 3 vector, which is like you can interpret as a velocity. But then the group equivariant, that can be another type of representation of the rotation group. So it could be, in other words, it can be a bigger vector, right? You have scalar, vector, and then we can go to higher order representations of the rotation group, which could be tensors, but it could also be bigger, longer vectors in some sense. And then it's very similar, right? Because in that space, we would also rotate, under a transformation, the pixel grid, which is what's happening here too. But we would also rotate, have a transformation on the actual capsule vector. That would also transform under a representation of the group, which is exactly what's happening here too. These vectors rotate under, in this case, very simple 3-dimensional rotation, but it could be a different representation. So it's actually very, very similar.
So I think I understand. But do I understand you correctly in that you're saying that that there is a difference, and that in one case, in the group equivariance case, you're rotating the pixel coordinates, and in this case, you're doing a rotation on the actual vector as you think of the activations in a particular vector space?
Well, I would say that the pixel, you should sort of the pixel grid, you should basically replace by this sort of graph here, a 2-dimensional graph, let's say, right? And the difference is, of course, a pixel grid is regular, and this graph could be in arbitrary, so these positions, X can be in arbitrary places, right? And so X, the actual position of that thing, is now a feature which you also take into account. So here you have Xi minus Xj, which is the distance between these two pixels, if you want, being taken into account when you formulate your messages. But otherwise, in both cases, you have a vector living on top of each pixel. Right now, we call that channels, for a normal neural net, because we basically we think about an entire image or an entire filter map, and as we just think of channels as different, sort of stacking different things. But if you look at one pixel, slice through one pixel, right, you see an actual vector there.
Right. So, but in group equivariant neural networks, you never apply a rotation matrix to that vector.
You do. You do.
Okay.
But the thing is, so for a steerable sort of architecture, you literally apply sort of a vector to that for a certain angle. If you have sort of a representation, a regular representation, then you can only do a discrete group. So you will just have to have, like, if you have like 4 90 degrees rotation, you'll have just 4 numbers in that vector. And then the rotation turns out to be a permutation.
Right. Yes.
But that's also a sort of a representation of the rotation group under 90 degrees.
Yes.
But in general, you can do irreducible representations, which just look like bigger versions of a regular rotation matrix.
That's super helpful. Thank you very much.
I'm sure everybody is super thankful to you that you asking these questions, because I'm sure if you don't understand it, there's many more that don't understand it.
Yeah, in fact, and thanks, Max, for these very, to go so deep in the answers, and thanks, Mark, for the questions. Yeah, and I know that Max is very happy to be stopped during the talk, but I will also give more shy people the opportunity to talk to Max after the talk. So
I'll keep a lid on it from now on.
No, please. I'm not saying you don't have to ask questions. It's just to give also, to other people, especially the shy ones, the opportunity to raise their hands and have questions for Max, and I'm sure he will be happy to.
Absolutely, go ask questions. I mean, I have more slides, but it's this is much more important to understand this stuff. So we've covered quite a bit of things now. So it's a good time to ask questions now. For sure.
No, please go ahead, and then we can stop and ask questions.
Yeah. Okay. I'll keep going, but if you have questions, please feel free to ask. I just wanted to mention two generalizations. So this is called the SE3 transformer. This is a part of the architecture. Well, a very similar kind of thing was presumably used in sort of AlphaFold, where also the term SE3 transformer was used, I think. And it's again sort of a transformer architecture where you look at your neighbors and you sort of use message passing, but the messages now have a very particular form, which is this query key kind of interaction. Also, in this case, we use not just three-dimensional vectors, but we use these spherical harmonic embeddings, which are higher order representations of the rotation group. We yet again sort of generalize that. I will not go into this in any detail, but you can read this paper, and it's a very general framework for equivariant message passing. And so here you can see, these are spherical harmonics represented as blobs. And here you can see as the neural network is processing information that these blobs are sort of changing. This whole thing is nicely equivariant. So if I rotate this thing, you will see exactly the same, but then turn around. So the second thing I want to talk about briefly is normalizing flows. In a normalizing flow, that's a different type of thing. So a normalizing flow is basically a problem where we try to generate points. So it's much more like an unsupervised problem where you're not trying to classify something, but you just try to generate points from a particular distribution. And so here we have a sort of a Gaussian distribution, and we're pushing this through a number of invertible transformations, like sort of illustrated here, to basically move the points into certain patterns that is the distribution of the data. So this is an invertible set of transformations, and this basically means it's a normalizing flow. You can write down the log likelihood efficiently, and you can do backpropagation on it, and sort of you can learn these components. So you can apply that to molecules. So you can just start with a whole bunch of molecules. They have different types, which is a discrete property. So you have to do something about dequantizing a discrete property into a continuous property. Then you apply some flow. In this case, we had an ODE type of model. And then, you learn this thing to assemble these points, to change their identity, but also assemble them into a realistic molecule. And this, if you have a large enough data set, you can basically sample some points and then assemble them into a nice molecule that's realistic. I'll skip this. There's some details, but here's a nice sort of illustration of what happens. It's all nice and equivariant. So, if I rotate the molecule, it has exactly the same property of being generated by this model. And so, I could have generated any of these orientations completely, with equal probability, right? And so here you rotate, and then the inverse transformation is what you see here, where you sort of disassemble things back into their latent space. And there you can rotate as well, although something weird happened there. Okay. Now we've also improved that method, and we sort of went to diffusion-based methods. We changed sort of the methodology slightly. Now we can already do quite a lot bigger molecules. This is trained on GM drugs, which is a database, and here you can sort of see that these molecules have, you know, between 20 and 30 perhaps atoms inside, which is already much bigger. And also the stability metrics that people typically use were much improved by this diffusion-based method. So what I'm seeing is that at every conference, these methods improve dramatically. And so we might see at times, if we have enough data, that we can really generate particular drugs with particular properties. So of course we try to do conditional generation where we specify certain properties and then let this thing generate molecules. The problem is that that's a very hard problem, and so we got, you know, somewhere, but not necessarily very satisfactory yet. So that's the next thing that we need to tackle, and therefore I think that's a very nice challenge for the community to go after. The last topic is PDEs. I'll just be very brief about that. So a PDE is basically a partial differential equation. You have the time derivative of some field is a function of time, position, field values, and their derivatives. There's some initial condition and some boundary conditions, and then you need to solve this, so integrate forward in time. So we basically just use what you would imagine you could use here, which is a autoregressive solver, which is you specify the fields at a particular point in time, you specify a delta t, and then you predict the value of this field at the sort of t plus delta t, and you learn a neural network to do that. So you need you need a accurate solver in order to to get the training data. So that's expensive, but once you have that, you can sort of train this neural integrator to then solve new problems with new initial conditions much faster. It's based on a message passing neural net, as I just proposed. I'll just skip the details here, but it is again, so here's the integration grid. The points are placed at certain random positions. You get messages being passed between the nodes, and it sort of it sort of accumulates an answer to what the value at that particular node is in the future. And you could, in principle, even move the integration grid points around. Some examples. Let me just go over this one. Maybe it's easier. So this is a ground truth Navier-Stokes simulation, and then here's the sort of the neural network simulator that produces basically the same result. But of course, it could do it much faster. Orders of magnitude faster, basically. And here's one where we do data augmentation. So these PDEs are very beautiful symmetries.
Sorry, Max.
Yeah.
About this previous slide, what symmetries are we observing here?
Oh,
or are there also equivariances in this case?
Yeah, so it's a very good question. So this neural net was just a graph neural net, so there was only sort of permutation equivariance, but there wasn't sort of necessarily a sort of geometric sort of rotation or flip symmetry that we used. But PDEs have very beautiful symmetries, which are much more general, in fact, than just sort of rotating or translating. They also involve the fields itself. So you have very intricate things where you could even take two solutions and combine them into a new solution or something like that. So it's a well-developed field, finding all the symmetries of a PDE. It's just very hard, and that's an open problem, to incorporate them into your PDE solver, so into your neural net, apart from the perhaps trivial ones. However, what you can do is you can use those symmetries to generate from one solution many more solutions. It's sort of data augmentation approach, and then use that to train your neural net, right? And that's what we did not here, but we did here. So these are new results for new neural nets. These are impressive basically because you can do very long rollouts and incurring very little error by your neural network numerical integrator. And that's because of symmetries. Yeah.
What do you mean with a data augmentation approach? Is it sort of you do transformations from the group, you sample them, and then you run them through this autoregressive solver, and then you
so
again or something?
So if you create one solution using an expensive sort of numerical integrator, for your PDE, you can then from that create many more solutions, because you know this problem has a symmetry, right? And let's say if it were a rotation symmetry, you could just rotate, you know, all the solutions that you have, right? You rotate them, and that's classical data augmentation, right? So you do from one image, you do a rotation, or you do a flip or whatever, and you feed it into the neural network as new data, and that will help you to avoid overfitting, etc. So same thing here, except for that the symmetries are actually more sophisticated than the ones that we're used to in neural networks. So they're not just geometrical; they also involve the actual field values itself.
Exactly. Okay. Thank you.
I also know Tigo. It's interesting. So lots of people here that I know. Okay, so this is sort of the end of my presentation. I just want to say that there is a very nice opportunity lying ahead of us, where in the natural sciences, in particular condensed matter physics, computational chemistry, and molecular biology, we can start to combine the techniques that have been developed in these fields with the techniques that have been developed in information science and computer science, like large simulation science, like computational science, it's called, machine learning, and in 10 to 15 years, quantum computing, which will also play an important role, because the best application of a quantum computer is a quantum chemistry type of calculations. And then, of course, there is beautiful applications in sustainability and energy and health, as I already mentioned, like a carbon capture, hydrogen production, clean fertilizers, biodegradable plastics, and health, like new vaccines, antibiotics against resistant bacteria, and immunotherapy. All of these can be sort of helped by understanding molecules better and assimilating them better and predicting their properties better. So basically, that's where I would like to end, and maybe leave the last 5 minutes for questions. So thank you.
May I ask a question?
Yes.
Please go ahead.
Okay. I am currently working on using SE3 transformers for potential energy modeling, and I would like to know your advice about it.
Sorry, it's a bit hard to hear what you say because there's a huge echo. So I think you have two devices on. Is this possible?
No, because I'm in a small room, so I'm going out. So
if you like, you can also type your question in the chat. Maybe that's easier. I can read it for you.
Okay, is it better now?
We can still not hear you very clearly. I think there's some sort of redundant noise.
Okay, maybe I can ask my question in email. Is that okay for you?
Well, try it one more time, because I think if you speak slowly, I can hear you. So go slow.
Okay. I am using SE3 transformers for potential energy modeling.
Yes.
So I want to explain why SE3 transformers are particularly attractive to us.
So that's a question, or is it?
No. We are trying to separate the long-range and short-range interactions, which have been partially explored in PhysNet. So long-range interactions are those that decay following some power law, and short-range interactions are quantum mechanical effects that decay exponentially.
Okay.
Is that clear? Can you hear me?
Yes.
The motivation is that the long-range interactions decay slowly, so they are only prominent in large systems. But during training, we only have small systems available because the ab initio quantum chemistry methods are not scalable to large systems.
Okay.
So it is hard to learn the long-range interactions.
Yes.
We are trying to predict the dipole and the quadrupole moment induction and polarization and van der Waals dispersion, and as well as the short-range interaction respectively. So we break the energy apart into long-range and short-range interactions.
Okay.
So now the long-range interactions can be computed given the predicted atom attributes, which generalize perfectly because it's just physics. Computing the interaction using the moments and polarization, etc. So you know the dipole moment is a vector, and the quadrupole moment and polarization tangent we need irreducible representation of at least degree 2. So we find SC3 transformer is especially attractive to us.
Okay, sounds good.
The problem is SC3 transformer and tangent field neural networks have been performed very poorly on modeling the energy surface. The SC3 transformer paper excluded this task. It included some tasks in QM9, but removed this task from the table, I think, because it just doesn't work. The error is quite high, so I would like to know your advice about it.
Yeah, so I don't know this particular problem, I should say. So I don't know precisely why this would not work, but it seems to be a very difficult problem that may not have anything to do with the SE3 transformer versus any other equivariant graph neural net. It may have something to do with the fact that you can only sort of train these models on small systems, and now you're trying to generalize this to a very large system, and with long-range interactions that is not seen before, and so it might not treat them very well.
But the problem is the performance of SC3 transformer is much lower than models that only state-of-the-art models that only use scalar and vector representations. I cannot understand why that is the case.
Yeah, I actually also don't understand that, but I've also observed that for certain problems, SC3 transformers are not performing super well. And I have to say, I don't know precisely why that is. So I don't have a real answer for you. Certainly, you know, it would be nice to figure it out, or, you know, make sure you use maybe the simpler E3 GNN models, which don't use the spherical harmonics and therefore also simpler and faster. So yeah, that sounds good. Actually, I need to run because I'm over time now. So
okay, thank you.
Yeah, so we should probably end here.
I would just like to thank again for Professor Welling for the very nice talk, and thank you for everyone to attend this meeting. Yeah, so since if I understand well, Professor Welling need to leave.
Yeah.
So have a nice evening for all, and yeah, thank you again, Professor Welling.
Yeah, thank you very much.
Thank you very
it was a lot
much.
of fun. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.